In the first talk in this series, I showed an example of vibration where I used a metal ruler clamped in a vise. Now, I used that to illustrate the idea that vibration has a frequency and that frequency is determined by the balance between restoring force and inertia, or between mass and stiffness equivalently. Well, one of the things I said in that previous talk was a bit of a cheat. I vaguely gave the impression that the vibrating ruler only had one frequency of vibration. It could only vibrate in one way. Well, that is not true. The ruler, like all these instruments you see in this picture, which ultimately is what we're interested in, can vibrate in many different ways. And that's going to be explored a little bit in this talk. A bit of jargon. Each particular way of vibrating is called a vibration mode, and each one is associated with a particular resonant frequency. The one we saw for the ruler and that I talked about was simply the lowest of these different frequencies, and it was the one that you could see most clearly in the video, but there are always higher frequencies. In this talk, I'm going to illustrate that idea and one key thing about vibration modes by using a vaguely musical example, but not a stringed instrument. What you see on the screen here is an idealized set of vibration modes for a drum, or the skin of a drum, a circular membrane stretched under tension like a string, but in two-dimensional sense. Now, here is the lowest mode of the drum. The whole surface simply goes up and down. That will be the lowest of the resonant frequencies, and that corresponds to the vibration of the ruler that we looked at in the previous talk. But as you can see in this picture, and this is just the beginning of a large set of things, the drum skin can vibrate in all sorts of other ways. Basically, it's a two-dimensional family. As we go along this top row here, the second mode here, you can see it's got kind of Mexican hat shape. It's going down at the edge and up in the middle, and then reversing, of course. So somewhere around about here, there is a circular node line. A node line is a point on the vibration where it's in fact not moving. So this has one circular nodal line. The next one along has two circular nodal lines. It's going up and then down and then up again. And so two circles. We go back to the lowest one but go down one. What we've got here is one nodal diameter. There's one diameter across the drum which is not moving, and it's going up on one side of that and down on the other side and then reversing. Going down one more. This one has got up, down, up, down. It's got two nodal diameters, and that series would continue off the bottom of the slide with 3 and 4 and so on. But that's not the whole story. We can get combinations of these. This one here has one nodal circle and one nodal diameter. One diameter and two circles. Two diameters and one circle, and so on. You get any combination of some number of nodal diameters and some number of nodal circles. Now, to illustrate that with a measurement, here are some animations measured on actually on the head of a banjo, but that's more or less the same as the skin of a drum. These are just two particular examples. Here's one with 3 nodal diameters. You can see as you go round the drum that it goes up, down, up, down, up, down 3 times. Here's one with 2 nodal circles, rather like one of the ones that we just saw in the previous slide. So real drums do something like this. Now, I want to use this drum example to make an important point about modal shapes and modal frequencies and why they're so important. And I'm going to do it with a link from this rather wonderful website, this falstad.com. We'll skip to it in a moment. You should explore this yourself. There are lots of other interesting things on this site. You go to the link that says Math and Physics Applets, and the one I'm going to use is called the Circular Membrane Waves Applet. And that takes you to this screen here. And if I click there, there you see an animation of that lowest mode of the drum, just like you saw in the still picture in the earlier slide. I clear that and then click here. Here's a mode with one nodal diameter, up on one side, down on the other. We go along a bit more. Here's the one with two nodal diameters, up, down, twice as you go round the circle. And you can see what I'm doing to make these. I'm clicking on the squares on this map here. So the next one along, you can guess, would have three nodal diameters. And there it is, and that's looking very much like that measurement I just showed on the banjo. Well, you can guess what will happen if I go down here. Now we get the one with one nodal circle, the Mexican hat mode. I clear that and go down again, we get the one with two circles. If I do places in between like this, then we get the combinations. This is the one with one diameter and one circle. All right, so far. So this grid of squares at the bottom corresponds to the plot that I showed earlier. It's actually got the axes organised the other way round, but nodal diameters along this way, nodal circles down this way, and any combination you like of them. Good so far. Lots of different modes, each with its own resonant frequency. But we can use this app to do something different. If I choose this option here to make my mouse into a drumstick, then I can go to somewhere and hit the membrane. And you see an animation in slow motion, of course, compared with a real drum, of how this drum responds to being hit at the particular place that I hit. But that's not the only thing that it shows. You see it's lit up all these red and green squares on the modal grid. Now, how has he computed this animation? It doesn't look like any of those mode shapes that we looked at before, but the remarkable thing, and that's the important thing we want to illustrate here, is that what you're seeing in this complicated transient motion of the drum head is simply a combination of a certain amount of each of those modes, just all added together. And that's how he's computed this shape. And the colours in this map show how much of each mode. Perhaps green for positive amounts and red for negative amounts, and brighter colours for larger amounts, and so on. I can't emphasise that fact too strongly. We've solved an apparently quite different problem here, the transient response of the drum. But if we know about the modes, that tells us everything. Let's clear that one and we'll do it again. So knowing the modes and their frequencies, we can calculate just by adding up contributions from all the modes. We can calculate the effect of applying a force at any particular place. Now let me illustrate hitting it at a few places. So here's the one I did before, a typical place a drummer would hit the membrane. If I hit right close to the middle, we get circles that spread out, roughly as you might have guessed, and the map of how the recipe by which those are made up from the modes has changed. If I hit very close to the edge, it looks different again, and the map is more rich. It needs a lot of the modes extending all the way to the edge here. We can even listen to it. There's a box here that says sound, and if I check that, now the animation will now be too fast to see, but you should hear the sound of striking this mathematical drum. So as you see there and hear, something that every drummer knows, hitting a drum in a different place gives you a different sound, and that sound is made up of a different mixture of the modes. Now let's go back to the slides and draw the moral from that. So the key points here: every structure, the drum, the metal ruler, a violin body, they can all vibrate in many different ways, which are called vibration modes. Each mode has a resonance frequency and it has a mode shape. We've just been looking at lots of those for the drum. Now here's the important thing: the total vibration response can be worked out simply by adding up contributions from all those modes. You don't need any extra information. The modes tell you everything. If you change the position or the direction of your force, what that does is changes the amplitude of each of the modes in the mixture, but it doesn't change the mode shapes or their resonant frequencies. The modes stay the same, you simply mix them in a different way. And that's the entire story of how structures vibrate. So that's why modes are going to be so important to us.